Hi, future scientists. My name is John, and today we're going to be building and experimenting with a fire tornado to try and understand what a nerve signal is and how it works. Today we're going to model a nerve signal with a fire tornado, and to really understand what's going on, we're going to talk about ions. We're going to connect things like voltage to pressure. And ultimately try and explain what an action potential is. And an action potential is just another word for the nerve signals that help your brain control your limbs and help you sense the world around you. The signals from like, touching and smelling and seeing that get relayed back to your brain. So the first thing I want to tell you about is ions. And an ion is just an atom or molecule that has a charge. And this could be something like sodium and potassium that have lost an electron, so now they're positively charged. It could be something like chloride ions that have gained an electron and now they have a negative charge. And it could also be something like lithium that's found in your cell phone battery. Now, voltage is the word used to describe different configurations of charges because, well, like charges repel. So if you have two positive charges that are close together and then they move apart, that's different. One's higher energy, one's lower energy. And scientists like a word to describe how those are different, how those configurations of charges are different, and that word is voltage. And it happens to be for things like two protons or two sodium ions moving from about 1 nanometer apart, a tiny, tiny, tiny distance, to 3 nanometers apart is about 1 volt. Here's another example of reconfiguring charges. If you take a lithium ion and an electron and some graphite, C6, and combine those together, that's a difference of about 3 volts. And just a third example, your cells. The human cells, especially things like neurons, regulate ions inside and outside of the cells. They have pumps and channels and transporters that move ions around. And here you can see that this is an example like sodium, where there's 15 times more outside of the cell as inside. That configuration of charges also sets up a voltage difference, a description of how that energy is different if those charges were allowed to move. All right. So that's what voltage is. It's a configuration of charges. Unfortunately, charges are hard to see. It's hard to, look at a single neuron and try and understand exactly what's happening in those cells of our brain and in our nervous system. So voltage differences can move charges and ions, and pressure differences can move liquids and gases. And I'm going to show you a couple quick demos to try and bring that comparison to life.
What you see here is a battery, and I have a wire, and I'm going to connect the negative end of this battery to the positive end. And this is a really weak battery. It's about 1.5 volts. And you can see there's a tiny, tiny spark. It's just barely a orangish glow. Don't try this at home. We're short-circuiting a battery. This is dangerous. The battery can overheat and start a fire. And now that's pretty weak. That's 1.5 volts. Let's try something bigger. Once again, don't try this at home, but now we have 4 9-volt batteries connected in series. So this is 36 volts. And now if I connect these, you can see we get a much bigger spark. We see a lot more electrons flowing between the two ends of this battery. So big voltage differences can result in a big flow of electrons and charges. Again, don't try this at home. So voltage differences come about from an arrangement of charges. Pressure differences can come about, in this case, by having a height of liquid. So if the height of the liquid is the same, I have a hole here on the side. If the height of the liquid is the same as the hole, not a lot leaks out. But if we have a column we have some height of liquid here above the hole, we get a little bit of pressure, and you can see that the liquid is actually flying out pretty fast. And as that starts to drain, what you'll notice is, well, the stream actually starts to bend less and less. It's coming out slower and slower. And you can see how weak and slow that is. And this is just like the 1.5 volt battery. We just had a really weak flow of electrons between the two ends. And next, what I'm going to do is fill this bottle up all the way and see if we can get a much stronger flow of liquid. All right, here we have a full bottle, and that's a lot of liquid up above this hole. And just like diving to the deep end of a swimming pool, there's a lot of pressure. You can feel it on your ears. And here you can see that big pressure, right? So instead of a really weak stream that was falling straight down, now we have a much more powerful stream. And this is just like the 36 volt battery that was creating a big flow of electrons, a big flow of charges that we could see as sparks.
So a voltage difference can move charges and ions, and we saw a little voltage difference moves a little bit of charge, and we saw just an orangish glow, and a big voltage difference moves a lot of charge, and we saw a bright white spark. The same thing's true with pressure differences. A little pressure difference, in this case from the height of a liquid, created a little trickle of liquid, but a big pressure difference from a really tall amount of liquid results in a really big pressure difference and a really strong stream. And now let's take this one step further. And I'm going to talk about a different way that we can create pressure differences. And that's with moving air. So this is sort of a fun demo that all you need is a strip of paper. So if you hold it just like is pictured and blow right over the top of the piece of paper, it actually lifts it up. This is just like an airplane wing, actually. Air in motion is lower pressure, and it can create lift. Yeah, cool. So that's one way to create a pressure difference. And the next one I want to talk about, we're going to do by rotating a window screen that I've woven into a cylinder. And, well, we're also going to add a little bit of fire. Please do not try this at home. What you see here is a rotating plate. I have a glass bowl in it, and it's filled with a little bit of isopropyl alcohol. And we're going to start it on fire. And what I'm going to do is add this screen to it, and we're going to get it spinning. And just like by blowing over a strip of paper before, now by rotating the cylinder, we're going to get air moving inside of it, and it's going to create a pressure difference. And in this case, it's actually going to oxygenate the fire. And we're going to see if we can take a little bit of energy from the fire and get it to propagate the full length of this tube, of the cylinder. Put on my safety glasses. Don't try this at home. I'm in a well-ventilated room. I have a second person nearby with a fire extinguisher. So here's my little fire. It's about, well, I guess it's licking up to about 12 inches, but it's around, I don't know, 4, 5, 6 inches on average. And if you spin a fire, whoop-de-doo, not a lot of but I'm going to wedge this in nice and tight. Whoa. When we spin this, you can see a little bit of fire down here actually gains energy. A pressure difference can feed it. And it grows. It's a little bit wobbly. Yeah, cool. Let me see if I can back it up a little bit. Yeah, cool. So here a pressure difference is creating a much bigger fire, but it's also directing which direction that fire spreads down the length of the column. So let me tell you again what we just did. We rotated that screen. The rotating air, it was also heated, created something like a helix that I'm showing with these red arrows inside the cylinder. That rotating and rising air was air in motion, and that has a low pressure. And there's relatively still air outside, and that pressure difference actually oxygenated the fire and created a fire tornado. And what's cool about that is that's just like what's happening inside your nerves. In that case, instead of a fire, it's a little bit of a signal. It could be from your vision, could be from hearing, it could be from a neighboring cell that's starting a signal. And instead of moving down a wire mesh cylinder, like on a screen window, it's moving down the length of the cell called an axon that carries these signals long range. And that's called an action potential. What's cool about these action potentials is that they can move really fast, up to 100 miles per hour. And where does this energy come from? Well, we know already that there's this potential difference because of how ions and charges are arranged inside a cell. More outside, more inside, depending on the type of ion that you're talking about. And that's a source of energy. But there's still this question of why is it so fast? Because each little ion, they're absolutely tiny. These are just single atoms. In the case of, well, things like sodium and potassium and chloride. And they're moving really, really slow. They're bouncing around with water molecules and other ions, and they're just moving at something like 10 nanometers per second. So how can they go millions of times faster to have a 100-mile-per-hour signal? And I'd like to show you that with just a quick little demo.
So here I have a paper towel tube. It's empty. And what I have is a bunch of ions that I've made out of tinfoil. And what I'm going to do is load this up with a bunch of them. And what you can see happen is that now that the tube is full, whenever I add an ion, well, one pops out the other side. And when I add one more ion, another one pops out the other side. And if I add an ion, one pops out the other side.
So what you just saw was tinfoil balls going into a tube. And every single ball that we put in there, the size of those tinfoil balls was about 3 centimeters. So as I pushed one in, it pushed its neighbor, and it pushed its neighbor, and it pushed its neighbor. And the speed of each ball was about 3 centimeters per second. 1 1,000, 2 1,000. I was just popping these tinfoil balls in the tube. But what's pretty cool is that once it's full and they're all in contact, colliding with their neighbors, that when I put that first ball in and this 11th ball pops out the other end, the speed of that signal, how fast one pushed into one end could force the other one at the far end to come out, was actually much faster, something like 30 centimeters per second if there was 10 balls. And you can scale that up if you just have a bigger tube, right? So here's a much, much bigger tube, and well, the sky's the limit. If you have something like an axon of a nerve cell that can be very long, extending all the way down to your fingertips and your toes, all of those ions colliding with their neighbors inside that tube, fed by the energy of that voltage difference, that configuration of ions outside of the cell and inside of the cell can keep that signal propagating or moving all the way along these really long tubes, just like a fire tornado, where a little bit of fire can actually travel a long distance fed by, well, not a pressure difference, but a voltage difference. Thanks for watching.